Hello everyone. Today I'm excited to share with you an interesting dataset that tackles one of the most significant global health challenges, obesity. This presentation aims to explore the datasets and its potential to provide valuable insights into obesity levels based on individuals' eating habits and physical conditions. That's all about. The dataset titled Estimation of Obesity Levels Based on Eating Habits and Physical Condition contains 2,111 records and 16 features. It categorizes individuals into various obesity levels such as insufficient weight, normal weight, overweight, and three levels of obesity. This dataset is derived from individuals in Mexico, Peru, and Colombia, with 77% of data synthetically generated using the Weka tool and the smoke filter, and 23% directly collected from users via a web platform. It combines multivariate data from eating habits, physical activity, and psychological attributes, making it suitable for tasks like classification, regression, and clustering. What is the importance of datasets? This dataset is important because it addresses a critical health issue that affects millions globally. By analyzing these records, researchers and health professionals can uncover patterns and relationships between dietary habits, physical conditions, and activity levels. Such insights can lead to developing data-driven intervention, promoting healthier lifestyle, and creating educational campaigns to reduce obesity rates. Furthermore, these datasets provide a rich foundation for machine learning application, enabling predictive models that can assist in personalized health management and policy making. Pre-process did you made? Before analyzing data, I need to pre-process the dataset. In this dataset, I use data cleaning and handling missing values, wherein data cleaning fixes errors and ensure consistency, while handling missing data fills gaps or remove incomplete entries. These steps are crucial for accurate and reliable analysis. Why the pre-process is important? Data cleaning and managing missing data are crucial for ensuring clarity and completeness in the dataset. Errors or gaps in data can result in inaccurate outcomes or mislead the model. By correcting inaccuracies and addressing missing values, the dataset becomes dependable and precise, laying a strong foundation for accurate analysis and reliable predictions. For the upcoming presentation, my focus will be on the evaluating the results of clustering and classification. The analysis will assess each technique's performance in terms of accuracy, interpretability, and practical relevance. Clustering will be judged on the cohesive of the groups formed and their significance to the problem domain, while classification performance will be measured using metrics like accuracy, precision, and recall. This comprehensive approach will provide a clear understanding of the method's effectiveness and their potential real-world applications. Comprehensive understanding of how these data mining methods enhance overall analysis and support decision making. It provides an overview of the performance of a classification model training using stratified cross-validation. This method ensures that each fold of the cross-validation maintains the original distribution of class labels, leading to more reliable results. The confusion matrix shows how the instances are distributed across the true and predicted classes. Here are some key points. Normal weights A. 244 instances were correctly classified, but 34 instances were misclassified as overweight level 1, obesity type 3. Near perfect classification with only one instance misclassified as obesity type 2. Misclassification mainly occur between adjacent classes such as normal weight being confused with overweight, overweight level 1 and obesity type 1 being confused with overweight level 2. The model demonstrates excellent overall performance with a high classification accuracy 93.75% and robust result across different weight categories. The confusion matrix reveals only minor misclassifications mostly occurring between adjacent categories. The model's precision recalls and F measure are strong for the most classes indicating reliable and effective predictions. The EM algorithm is a probabilistic clustering technique that models the data as a mixture of Gaussian distributions. It iteratively estimates the parameters of these distributions to maximize the likelihood of the data. The set was clustered into 8 distinct groups using the EM algorithm, capturing validation in obesity levels, age, gender, and lifestyle factors. Key clusters include individuals with normal insufficient weight and severe obesity. Factors like eating habits, physical activity, and family history strongly influence the cluster formation. Data validation check for missing values and outliers in critical features. Cluster analysis. Label cluster for interpretability. Target specific obesity intervention strategies. Visualization. Use graphs to better understand cluster separations and patterns. Clustered instances. Final distribution. Cluster 0, 83 instances, 4%. Cluster 1, 373 instances, 18%. Cluster 2, 479 instances, 23%. Cluster 3, 281 instances, 13%. Cluster 4, 229 instances, 11%. Cluster 5, 207 instances, 10%. Cluster 6, 222 instances, 11%. Cluster 7, 237 instances, 11%. The dataset was split into 8 clusters with the percentage of data points per cluster, ranging from 4% cluster 0 to 22% cluster 2. The clusters vary in size, which indicates the algorithm successfully differentiated between distinct subgroups within data. This categorical variable represents different obesity levels. Clusters reflect different patterns of obesity levels. Cluster 0, mostly normal weight and insufficient weight individuals. Cluster 1, predominantly obesity type 3. Cluster 2, large mix of overweight level 1, 2 and obesity type 2. Cluster explanation. X-axis height. The x-axis represents the height in numerical format, likely in meters. Y-axis. The y-axis corresponds to the nominal class, which represents the different categories of weight or obesity level. Color legend. Blue represents individual with a healthy weight range. Cyan, individuals in the initial stages of being overweight. Green, individuals with more advanced overweight levels. Red represents the first stage of obesity. Pink, more advanced obesity. Yellow, severe obesity or morbid obesity. Purple, individuals below a healthy weight range. Observation of clusters. High base separation. Taller individuals are generally classified as normal weight or in higher weight classes as seen on the right side of the plot. Shorter individuals appear in the categories like insufficient weight or higher obesity levels. Distribution across classes. Each weight class from distinct horizontal bands on the plot. This reflects how different categories are associated with particular ranges of weight and height. Overlap. There might be some overlap between categories like overweight level 1 and normal weight, indicating potential similarities in height among these groups. Recommendation. Data validation. Check for missing values and outliers in critical features. Cluster analysis. Label clusters for interoperability and target specific best intervention strategies. Visualization. Use graphs to better understand cluster separations and patterns.